Welcome everybody, and I'll turn it over to Paul.
Hi guys, I hope everyone can hear me okay. As Mary said, my name is Paul Rodriguez. I'm here at SDSC. I work on Exceed projects. Today I'm going to give just sort of a broad introduction to neural networks, kind of, assuming people don't really have a lot of deep experience. So I'll do an overview. I'll talk about convolution networks, which is really the hello world of deep learning. And we'll talk about, we'll do a demonstration with this particular task called MNIST using the Keras package on Expanse. And then I'm going to try to save some time for considerations of workflows. So I won't do a lot of demos at that point, but we'll talk about just how you might want to organize your jobs and your tasks and your processes. Okay. So I always like to start a general introduction to neural networks with logistic regression. And I'm going to assume that everyone here has some introduction to either statistics or math or machine learning or regression. So in the logistic regression, we start with the logistic function, which looks like this. And it has a particular shape and a couple parameters. And in typical regression and machine learning frameworks, we have to learn what these parameters are. The function looks like this. In this case, it's a squashed function. The output can go from 0 to 1. Hang on a second. Okay, and the thing to think about when we do neural networks, all we're doing is taking our regular kinds of functions, and we're going to create, you should think of it as sort of we're doing this graphical depiction. And in this picture, we've taken our function and we've turned it into a node, and there's some output, which is the f of x, and there's a bias term. We call it a bias term, but you could call it a y-intercept in the regression framework. There's an input, and it could be a vector, it could be a variable, it could be a matrix. We could have different kinds of inputs with different shapes, and there's some parameters which we call weights. And so we're going to use a kind of terminology that says there's a unit or a node. Sometimes it's a neural node. We're going to transform the input into output with some particular kind of activation function. In this case, our activation function is the logistic function. And of course, again, the idea is that given some data, and I didn't tell you what the shape of the data, how much data, it's the matrix, what kind of data, and given that we know what the outputs are, we're going to find parameters so that the output, in this case, the logistic function, is going to equal 1 when y equals 1. So in a classification framework, you're outputting, let's say, 0s or 1s. In a regression framework, we might be outputting a real value, and then you wouldn't use a logistic function, you could just use a linear function. Okay. Hang on, I'm trying to, okay. Oops. So just real quick, so we have this function, and the parameters that we have in this case can change this function in different ways. The weight parameter on the input can change the slope of this function. The other parameter, the bias parameter, changes kind of where that function is located. So you could create all kinds of variations. I mean, we could change the sign of W, and it would change where the high values are, where the low values are. So there's some flexibility depending on these parameters. And the reason that's important is because with different kinds of parameters, we can have all kinds of different functions. We can have very smooth, very sharp ways, and as I said, we can have it going up or down in different directions. And the nice thing is, the trick of the whole, maybe the main trick about a neural network is that we're going to repeat this function over and over again. We're going to take a lot of units, and we're going to combine them. So imagine I have two different functions, and let's say it's actually working on the same input. Now I can take these functions and I can add them together. We could say, well, we're going to add them, and we're going to call the next layer a function of the next set of functions. We're going to call it like a hidden layer. And if I ask you to take those original functions and add them together, well, what do you get? It turns out you get something that looks like this. So what happens is I shifted these functions a little bit with these parameters. So I placed them in a certain way. So when I add them together, I get this nice bump function with the center at 0. Okay, so that's kind of cool because you could, create lots of variations on this. And in fact, if you can keep combining things, so I was just playing around with the function, you can create all kinds of interesting combinations. So here it looks a little bit more like maybe a sine wave or something like that. And if you know something about function analysis, then creating flexible functions basically means you can really represent any function. So multi-layer networks in general can represent any logical or real valued functions. We sometimes call it unbiased because they have the ability to fit any function. But when you create functions that, like a neural network that's nonlinear and unbiased, they also have a lot of potential to overfit. And as you might guess, there's also a lot of parameters to fit. So that's the upside of the neural network and the downside of the neural network in a nutshell. Now, once we get used to comfortable thinking about the fact that these nodes, when I draw these nodes out, well, these are individual functions and they're all, going to be defined with some activation function, and all these arrows are representing inputs and outputs, we can organize these things in a neural network. So the multi-layer perceptron is basically a 3-layer network, although sometimes people might use it for more than 3. We typically say multi-layer perceptron is a 3-layer network where there's input, hidden, output layer. And sometimes people use the word dense network to be more generally feed-forward networks that have many layers. Okay, so we have an input layer and a hidden layer and output layer. Again, the input layer can be vectors, and it would be, if you have a matrix with a certain number of features, let's say it's a, n by p, you would have individual observations, or one row of the matrix would be your input. Your output would be one or more output values. So it could be a multivariate output, it could be a single output. And of course, when I draw a network like this, each line is basically a rate parameter. I'm not drawing a bias, but each node is also going to have a bias parameter. And once you draw that, you could say, well, when I run a neural network, I can build many layers. I don't have to have just one layer. And really, in the algorithm, the first step is to choose. You're choosing layers, you're choosing connectivity patterns, you're choosing activation functions. And then the algorithm starts by doing a forward propagation step, and that's where you take your input, you apply it at the input layer, you calculate the hidden unit activations at the second layer, you go forward to the third layer and the fourth layer and so forth. So we call that the forward propagation. And then for modifying the weights, we're going to do a backward propagation. And in that case, we're going to have some kind of error function. Now, typically the error function is usually straightforward. If you're doing classification, you might say, well, I expected a 1 or a 0 for a particular variable, output variable. And so my error is going to be maybe 1 minus whatever got predicted. For regression, it's going to be something similar. It's going to be a mean squared error. But once you have an error function, then you can combine that with other kinds of parameters to create a loss function. So we usually say a loss function is the thing we're using for backward propagation of derivatives, of information. The loss function is really mostly an error function with some other extra stuff. Sometimes it is just an error function. So generally we talk about loss functions. And when we have some output and we have some targets, we have some values that we're trying to train the network to predict or to output, we take the derivatives and we can pass it back to the previous layers using a chain rule. So without going into details, it's really kind of an indexing nightmare, because you have to look at the output. I don't know if you can see my cursor, but the output at each, let's say, node at the output units, that gets, the contribution to an output comes from all the hidden units. So for any hidden unit, you have to look at each of the output units it's contributing to, and then you have to go back to the previous layer and look at for all the hidden units, for any hidden unit, look at all the units it's contributing to in the next layer, and so forth and so on. So the backward propagation is really, the computationally expensive thing that's going on. And the other thing to be aware of is as you get deeper and deeper networks, as we get more layers, the error signals tend to get diluted. And this is called the vanishing gradient problem. So this has always been the issue for neural networks. We have a lot of parameters. We like the idea of having number of layers because that kind of adds to maybe flexibility of our functions. But the error information has to go back into more and more layers. It goes farther away from where the actual derivative started. So your information gets diluted. Okay. So anyway, this is just showing you a summary. In summary, this is basically the algorithm. Though there's forward propagation, backward propagation. There's a formal way we update weights. So the algorithm, in summary, I'm going to restate it here. It looks like this. We initialize our weights. We typically have small random values. We have some looping set up so that we do a forward propagation. We get all the node activations, calculate derivatives, we update weights. And then we stop when the validation loss reaches some minimum or converges. So if we stop updating weights, then we know we should stop. Or if we have a test set, a validation test set, where we can check and see how the network is doing against something it hasn't seen, then we would stop when that validation loss reaches its minimum. Okay, so I'm not really going to go into too much of these kinds of I mean, there's a lot really for each of these steps, of course, that's going on. But if you've done machine learning, this kind of layout of an algorithm, a lot of algorithms really have the same basic structure. There's some initialization setup step, there's some looping, there's some weight up or parameter updating, and then at some point you stop. Now, the thing about deep learning and neural networks today is that all these steps have some variations or some specifics that help you either make it faster, make it work better, make it more computationally feasible, so that you can do larger networks. And that's a lot of the name of the game when you're actually running some of these deep networks. And another important development in the last several years is that instead of using logistic activation or linear activation function, now we have different kinds of activation functions that also make this make the whole algorithm work faster. So the rectified linear unit is a nonlinear unit, but it's piecewise linear. So I'm not going to go into the details of this, but it has some nice properties. It's unscaled, so that's potentially bad because you're no longer going to get a 0 to 1 limit. But the derivative is constant, so that's good. So as long as you can have some ways to deal with the potential unscaling issue, then this turns out to be a really good function to use because the derivative is so easy. And it turns out one thing people do is, we'll look at this when we do the convolution networks, but there's some way you could look at the activations and either you normalize it or you summarize it with a maximization operation. So people have discovered that this is a really, this kind of activation function is really feasible. It works really well, and we can, mitigate any issues it has. Okay, and the main thing is this helps with the vanishing gradient problem.
Okay, so the summary for this, what neural networks are about. They're general or flexible. They're powerful learners. They're doing linear, nonlinear transformations of input. There's a lot of heuristics about what works and what kind of things are good to do. The bad side is that it's sometimes hard to interpret. You really do want more data, especially compared to other kinds of models. And there's lots of parameters. All right, so what is deep learning? I think I already gave you a hint. Deep learning refers, in some sense, it refers to just learning complex, varied transformations of the input. Another way to think of it is that it learns to discover useful features of the input. And in the neural network context, we sometimes say deep learning is a neural network with many layers. That's kind of the simple definition. But really what's going on is the first two things. All right, so convolution networks. So convolution networks, again, it's kind of the the MNIST problem is the hello world. It's typically applied to image processing, but you can use it for other kinds of spatial temporal problems. So there is a database called the MNIST database. It's been around for a long time. It's a database of digits. And the main task is, well, how do we classify digits? So I want to just zoom in on an example, and we'll go through what the convolution network is about. So here's the number 7, and what I've done is just I just zoomed in to the 7, and I'm showing some, I've just normalized all the values to go between 0 and 10 just for this example. So let me zoom in again. So if I zoom into a part of the 7, it looks something like this. There's high values of 10 right around the edge. There's some lower values, 3, 7, 9, for example. And if I zoom into this, so what we want to do is take a patch of this image at a time. So I drew here a 3x3 box, and we're going to call this let's say our filter block, or the size of our filter. And we're going to produce a function over this box. And I'm going to start with this filter, which consists of just -1s on one side, 0 on the middle, and +1 on the right side. So this is a predefined filter, and if I run it, we'll see what it does. So we multiply element-wise this 3x3 patch of pixels with the 3x3 filter. We can call this our weight parameters. And we're going to put that answer into a new output box or output map. So this particular patch times this filter gives me a 3. Okay, so it's image patch times my weight. Then I'm going to slide my patch over to the right. I'm going to repeat this operation. And I end up with a 7. And I'm just going to keep doing that. The next one is a 3. So sliding the filter is basically a convolution operation. And if I keep doing this, I end up with a new output map. So it looks something like this. I have a range of values in this output map. The output map is a little bit smaller than the original. And now I can and I can ask, well, what are the highest values represent in this output? Well, if you look at where the highest values are, 21 is the highest value, and 17 and 15. So this is basically the edge of the number 7. So when you get in high values, you're getting something that's matching my filter. So the filter is saying, look for changes in values as you go from left to right in a vertical direction. So we have another next step that people have found is useful, and that is to say, well, let's take a maximum over a certain amount of this output map. So a typical thing people do is to say, well, let's look at 2x2 filter, a 2x2 patch, and we'll take a maximum. And in this case, the max is 17. And we'll just slide that filter and keep going. You end up with you started out with a 5x6 patch, and now we've transformed it into a 2x3 feature map that represents the edge gradients. And this is the basic operation of what a convolution is doing. So in computer vision, there are many kinds of filters that you can sort of look up, and people have suggested this is a good way to filter an image. These are good little, things that you would multiply against your patch of pixels. But building features is kind of hard. It'd be nice if you could learn this, and that's the beauty of the convolution neural network. So in the convolution neural network, the filter values are the weight parameters, and they're going to be learned. So in some sense, you're doing, this is the feature discovery part of deep learning. You're not deciding ahead of time, well, what kind of edge do you want? You're just letting the network figure out what should the features of your little image patches be. So a convolution layer is a set of feature maps where each map is derived from a convolution of one filter with the input. So that's the other key, is that we're going to repeat this operation for a bunch of different filters. And we end up with a bunch of different feature maps. So the downside is, as you might have guessed from what we said before, is that there's going to be more hyperparameters. So we have to think about, well, what are the size of the filters should be? And in general, smaller is better, or more capable, more flexible. How many pixels should we slide over? Usually people use 1 or 2. The more pixels you slide over, the more computation you save, but you're losing granularity. The number of filters. So the number of filters is really like the number of features. So if you have 10 digits that you're trying to classify, you should ask yourself, well, how many features do I think I need in order to classify 10 things? You probably need at least 10, but maybe you could get away with, 4, because all combinations, what are there? 2 to the 4 is 16. So maybe, 4 features that are either on or off could represent 10 different digits. So that's kind of how you might think about how many filters you want. And then whether or not you're going to use max pooling. Usually people use some kind of pooling just because it saves computation and you're not really losing much information. Okay, so let's look at what a big convolution network looks like. So here I have an image, and it's going to have some height and weight, and 3 is the depth, because for a color image, there's 3 channels. And typically you start with some images and you're going to crop them so that they're all the same size. So in this example, this image is 224 by 224 by 3. So that's your image. And then you're going to say, well, let's pick a filter. And in this example, I choose the 5 by 5 by 3 filter. Okay, so the 3 at the end is because you have 3 channels. The 5 by 5 is going to be height and weight of height and width of your little patch. Okay, so that feature map that gets output is going to depend on the size of the filter and the slide parameter. So we're going to end up with this filter, we end up with the feature map. And then we're going to repeat this for a bunch of filters. We're going to say, well, let's take, I don't know, we'll see. I think in this example they took a couple hundred. I'm not sure. We'll see how many filters this actually consisted of in the network this came from. But we're going to repeat this for many filters. Each filter is 1 feature map. We're going to stack the maps. So now we have a convolution layer that consists of all these feature maps. Okay, and so again, the thickness is the number of different feature maps. And again, we might call this channels. Sometimes it gets called filters. I think more properly it's called filters. Sometimes you'll see it called channels, like like the original input was. And then we're going to decide if we're going to add another convolution layer. You could add a max pool layer down here, or at this point to the downsample. And if you keep doing this, you end up with a whole stack of convolution layers. And so for something like this, this became feasible when you had GPUs. There are now people collect a lot of data. So these kinds of large networks are becoming more commonplace for sure. And this example, let's see. So that started out with something like 96 filters in the first convolution layer, and then 256 in the next one, 384, 384, 256. And in the end, the final layers are just the final convolution layer gets flattened into a vector, and that gets passed into just a multi-layer perceptron in the last 3 layers. Okay, so at the end you have these dense layers just to combine the features into some final classification. So this is this was the AlexNet. It was run on an image classification problem with 1,000 images, or sorry, 1,000 classes, and I can't remember how many images. A large number, maybe 1 million images or something like that. And this comes from the, this Vision conference that has this competition every year, or used to. Oops. Okay, so now we can ask, well, so this is the kind of thing that works. This works a lot better than just trying to build your own filters and run it through a machine learning problem. And what convolution, you can look at, see what comes output, what the convolution layers look like, and that's what we're going to run in the demo. Your lower convolution layers tend to be simple filters representing, either edges or combinations of edges or colors. And as you go up in the network, as you look at the convolution weights and the activations, you get to, you start getting more and more abstract representations that represent classes. So that's the whole, in a nutshell, that's the whole idea of what's going on with these convolution networks. So they work because the convolution layers are really kind of like special architectures. It's like kind of biased to do a kind of transformation around a little patch. The lower layers, you have less filters for local features of all classes. Higher layers, more filters that cover more of the space of your image, and they tend to represent object class features. Okay, so I'm going to just pause real quick. I'm going to switch over to, what I'm going to do is run a demo. Oops, okay. Okay, so let me actually, before I get to the demo, let me summarize. So what I want to do is switch and summarize. Well, let's see what the actual code looks like to run this kind of thing. So I have a Python notebook, what I'm going to show you in a second. But before I show it to you, I'm going to just summarize it real quick. Basically, when we're running neural networks, we have, for every model, you're going to have just kind of 4 basic steps. You're going to load your data, prepare your data. We're going to define a model, fit a model, and then test the model. Okay, so here in this example, this is the whole code to run this particular MNIST problem. So Keras is a TensorFlow application that is built to help you set up your model. It's kind of like a high-level library for neural networks. And the way Keras works is you have a model class, and you basically define the kind of model you want. And for something like MNIST, we're just going to use a sequential model that feeds from input to the next layer, to the next layer, to the next layer. We're going to say, okay, we're going to flatten the image into a vector. Okay, this is actually the multi-layer version. Okay, so this is a real simple one that's not even using a convolution network. All right, so I'm going to skip that. Oh, here it is. Okay, so here's the convolution network. Here's how you define the convolution layer. You have to tell it the number of filters you want, a kernel size, which is basically your filter size, how you want to stride over, the activation. One thing that's important to keep in mind with Keras is you don't have to say how much input you have. You tell it the input shape, and it assumes you're going to have some number of observations. So it'll kind of figure out that first dimension of your input matrix. Okay, and so in my demo, I'm not going to go through this, but you would do this on Expanse. You could go to the Expanse website. There's a Expanse portal link. If you go into the portal link, you have a way to get interactive applications, and there's a Jupyter Notebook option, and you would start a Jupyter session, and it has a bunch of parameters you have to enter, which are basically you're running a job interactively. So this is the same kind of parameters that you get in a Slurm job. And let me switch screens and show, oops, let's see, where am I? Here it is. Okay, so here I have the MNIST program. It's the same one I was just showing you in the slides. It creates a sequential model, sets up a couple convolution layers. There's a max pooling layer, you flatten it, and then you do a classification layer. So I'm just going to run everything here. Okay, and if you're familiar with a Jupyter Notebook, every time you hit run, it shows you to the next cell. So this is, by the way, when you define a model, you can do a model summary. It shows you what you have, your output shape, the number of parameters. If I run this, okay, it's going to run in several seconds. So I'm running with something like 60,000 images. I'm running this on a compute node. And the nice thing about TensorFlow is when you run on a compute node, it will use all the cores. So for small problems, you could use a shared node. I typically find it's nice to just use a full node. And in this case, it looks like it's taking 11 seconds for every epoch of training. So that means it's going through all 60,000 images in about 11 seconds for those 25,000 parameters in this model. And it's gonna run, and it's gonna, you know, have some accuracy values. It's keeping track of the validation of the loss value for both training and validation data. And so I'm just going to let it run, and then we're going to show you a couple things. Okay, I'll show you the code a little bit. So here, the nice thing about Keras, you know, Keras is very flexible. It's built to be, you can customize it without too much difficulty if you're comfortable with Python programming and some of the object-oriented formulations. So in the Keras, I have a model that I've defined, and then I have to tell it what kind of loss function I want, which optimizer to use. So there's a lot of variation on optimizer. I tend to use the Atom optimizer, which is kind of a little bit more current. SGD is stochastic gradient descent. So this is the basic using derivatives in the backprop optimizer. You sort of compile. The compile is really kind of just assembling all the pieces. There is a way to tell the model when to stop. It's called early stopping. And you have to, again, you create a function definition. You say, okay, I'm going to use the early stopping function with these parameters. Your fit function is basically running the model. You give it your training data, some validation data. You tell it the batch size and these other options. And then you can evaluate your model. So that's the basic flow of running a neural network in TensorFlow. Okay, so this part, so the training is done. It gives me some, let's see, this is like loss and accuracy. And now I'm just going to show you a couple things. So you can plot the information. So the fit function returned a history of everything that happened while it was training. Okay. And
Paul, can I
yes.
real quick ask, somebody wants to know if this is running on CPU or GPU?
This is CPU. This is a compute node.
Okay.
So I got a compute node through the interactive session. On a GPU, this would be much faster. I'll talk about that towards the end.
Okay, thanks.
Okay, so I just want to show you, this is, again, this is an easy problem. 60,000 images are quite a bit for just 10 classes. So it learns it very quickly. Again, I'm not using a very deep network, so the performance isn't great. And I have just a couple, so I'm not going to go through the detail of this code, but I have some code that will show me, it'll show me the filters. So 3x3 filters, again, there's no obvious, this one right here, maybe that's doing like an edge detection, right? Because low values here, higher values on this side. So it's not obvious when you look at these filters what they're doing. You could look at the activations. Again, Keras has these ways to when you run the model to save outputs. And so I gather the outputs, and I'm just going to plot them in a mosaic. That's what this code is for. And so this is the activation of the convolution layer. So these are my 16 feature maps, because I asked for 16 filters. And you can see it takes the input, which in this case was a number 5. And some of these feature maps don't really transform it too much. Some of these transform it quite a bit in different ways. Some of these seem to really just highlight one part of your input. So it's very tempting to look at this and say, oh yeah, I can see what these feature maps are doing. But that's the kind of thing you might do as you run a network for something like an image processing. Okay, so as an exercise, if we had more time, I would suggest you play around with the number of filters and the kernel sizes. If you use large kernel sizes, you'll get different kinds of filters and feature maps, and you can see whether or not it's producing something you might say, oh yeah, that's the part of a 0 or that's the part of a 4. Okay.
Oh,
yeah.
We have a few questions. Do you mind if I just chime in real quick?
Yes.
So one was, can you share the code? Can you share code?
Yeah, that'll be available with the slides.
Next is, could you elaborate on batch size and how it is determined?
Yes, let me do that in the next slides.
Okay. Do you want me to read the rest, or you want to?
Go ahead.
Okay. Next one is where can we find the account name to start a notebook session? Is it the username?
You would when you start a notebook session, that's going to be your no, that's going to be your it's going to be your account. If you have a project account, otherwise I guess it would be
That's your allocation account.
the allocation account. Yeah.
Yeah. And that would, I think, Paul's, if you log into the Expanse portal, it will, and you use the Jupyter Notebook launching form page, it will already know who you are. And there's a place where you'll enter that account, allocation account, and then it'll launch the job for you.
Right. That's right. Yeah, if you go to the Expanse portal page, it's actually pretty straightforward. Okay,
I'll hold off to the rest of it and let you finish up, and
Yeah.
then I'll bring it back in.
yeah, because I think some of these will be answered.
Okay.
All right, so here's the thing we want to think about. So let's say you're at the point where, okay, you set up some code, you get comfortable with what Expanse is doing. And here's the things you really want to think about as you run on really whether it's Expanse or anything on Exceed, for your project in general. One of your big time things, your big time considerations is going to be choosing hyperparameters. So when we choose our hyperparameters, it's really a little bit of exploration and exploitation. You need to figure out how to, and I'm going to go through these in a little bit more detail. We need to figure out how to run efficient jobs. CPUs work fine for many cases. If you're doing multi-layer perceptrons, if you're not using a lot of data, you could get away with CPUs. The bigger your networks, the more data you have, then you're going to want to use GPUs. As you get to really big jobs, I'm not going to talk about really big jobs because that really takes us to a different level of detail. But you would always want to consider, using model checkpoints, model saves. TensorBoard is available, but it takes a little bit of to run it in a secure way. It takes a little bit of extra work here. So if you're in that mode where you really want to use TensorBoard, let us know. We can point you in the right direction. Okay, choosing hyperparameters. So this is really, I think, maybe the hardest thing. Not the hardest. In some sense, it's easy, but it's maybe the most time-consuming, or one you really want to think about. It's hard to find the global optimum, the absolute best set of hyperparameters. You're typically going to find something that works well, and then around, then you're like close to maybe what probably is some optimal. And I always recommend start with small data, do short runs to get a sense of a range of good parameter values, whether it's like number of layers, number of units. Those are the main things that are going to affect how big your network is. Maybe the thing to do is to start with a small data set. Make sure you can train your data and maybe overfit it. So the network, at least give the network enough resources so that it can learn your data, and then back off by starting, going with less units or less layers. Consider layer. How many units should you have in a layer? Well, it should be around the same size as the input. Some people used to say, oh, it should be, a third of the input size. There's really no hard and fast rule, but if you start with the number of units equal to the number of your input, well, it depends. No, that's not even, I don't know if that's even a good rule. In a multi-layer perceptron, that could be a good rule. With some of these, image processing stuff, again, think about it in terms of number of features. And then, the other ways to regularize is, maybe have different loss functions. Try to get more data is always a good way to avoid overfitting. And once you get to that point where you sort of have a sense of what is a good number of units or layers, you want to do an easy method to find your best hyperparameters is to do a grid search over uniformly spaced values. So, 1 layer, 2 layer, 3 layer, or 10 units, 20 units, 40 units. And so once you find out what is a good range, then maybe you start narrowing your search more. So that's the exploitation part. The exploration is the wide search, exploitation is the kind of the narrow search. But there are, okay, so generally, I think of it as like there's architectural parameters, like layers, units. There's algorithmic parameters, learning rate optimizer, epochs. There's really good heuristics or good advice. If you look at what people have done for things like learning rate and optimizers, like the Atom optimizer, I think seems to be like the latest and nice, maybe the most flexible, because it adapts to learning rate, it uses momentum, it does these different things. So you don't want to necessarily spend a lot of time trying out different optimizers, because you're probably not going to get huge difference if you use, I think, the Atom one, and it's 80 AM. At least that's what I find in practice. There are some things like that help you with efficient learning, like batch size, weight or layer normalization. I'm sorry, not weight, activity normalization, initializing weights with certain kinds of distributions. So these are more related to just making your learning work. They're not really independent from a good network. So batch size could interact with some fashion so that you have good learning. There's batch size and there's shuffling that kind of interact together. But in general, your batch size should be as big as can fit in memory, because the bigger your batch size, the more efficient your network will run. Because TensorFlow will work on forward propagation and backward propagation. It'll work on each individual part in batches. So the more you can batch, the more it can just do one big calculation, save all the activity, figure out what it needs to do for backprop, and then that's batched as well. So that makes a difference in that sense. So I find well, again, it depends on how big your data is and how big your network is, what a batch size is. When you're using GPUs, you want to use batch size that are multiples of 32, because GPUs are doing things in vector CPUs work in blocks of 32. At some point, a big batch size maybe doesn't make as big a difference, though. So I don't have a hard and fast rule, but people sometimes you do have to use something like just small, like 32 or 16, and sometimes you can just fit 512 as your batch size, or 1,000, or even more. Okay. All right. So this is just these are things you have to go through, but when you're setting up your network and your parameters. But it's always good to also look and see what works. And maybe you find like someone who's got recent set of recommendations. There's a lot of blogs out there that some of them are pretty good. Some of them, maybe they're a little bit older, and it's hard to know. The literature is still moving fast. There is a hyperparameter tool called Keras Hypertuner. I have some examples in this slide. I'm not going to go through the details. I find that if you set up a hypertuner, it can save you time, because it's working, like, depending on the kind of search strategy you use, it can be a little bit, it can be more efficient. So it's kind of nice. If you're doing something that's not too big, maybe you'll just do a grid search and just it'll be fine. Okay. So this is just how you set up a hypertuner for your code. This is just a code snippet. I'm not going to go through in detail. The other thing to think about is your workflow for your jobs. You really got to think about what makes sense. Because you're going to want to be doing, if you're doing a big network with big data, at some point you're going to move everything to batch, and you're going to want to set up a Slurm script. And you can find those examples off the Expanse user guide. And you really got to think about, well, how big, how much do I want to put in a job? You want to kind of organize your work so it's easy to see, like, okay, I've run this set of networks with these parameters, this set of networks with these parameters. Do you want to, so at the level of a model, you're going to run and test the model for each set of parameters. At your data level, you're going to maybe do a loop through cross-validation. So, how do you want to set up a job? Is it one model and one configuration, or is it one model and 10 configurations with 10 data sets? So you kind of need to think about what makes sense. And really it also depends on how long everything runs. So it's hard to know in advance, like, what's the ideal way to set up a workflow. But it's really, it's not particularly, it's not the most, mechanically, it's not hard to do. It's more like you just have to try out a few things. Okay. People like using this YAML these days. So, I go back and forth. Sometimes I use something like YAML where I take my parameters, I stick them in a text file, and then every time I run, I say, run this job, point it at this YAML file, and then go. And then I just have to change a YAML file and run the job again. And then I just have to save my YAML file with my output. So, when you organize your workflow, just set up a nice way that you could either use a YAML. Sometimes I still just use arguments. I'll just pass arguments to my Python script and make sure I save what those arguments are. Because when you start running into a lot of these things, you want to keep track of which were your good parameters. Sometimes you might try a different data set for some reason, and you want to just make sure you put that in a different directory or something like that. So it's good to have your parameters, your code, your output kind of hang together in directories, and that's really what you want to do, set up in your workflow. Okay. All right, so here's a sample script in Expanse. I'm not going to go through this in detail. Again, if you haven't seen Expanse, Slurm jobs, or any HPC Slurm, this is just a basic Slurm job that would work. It works very similar for Expanse or Bridges or some of the other Exceed resources. In this example, I'm setting up to run a Singularity image. So on Expanse, we have some Singularity images, and it looks, when you run it, if you look at this section of the Slurm script in the middle, it looks something like this. You've got a command to run an exec. There's a bunch of Singularity images that have different TensorFlow versions in our CM shared apps directory. That's part of our SDSC environment. So this is one way to go. The Singularity images are nice because they're set up. And if you're going to use GPUs, you're going to want to look at the TensorFlow images that are set up for GPUs. The latest one, I think, is going to be set up to works on GPU and a CPU. So if you go to that directory, you'll see what the images are. If you're doing something that doesn't need more than different GPU devices, then you could also set up your own environment. Or if you're comfortable with setting up Python virtual environments, that's another way to go, because then you can put into your environment whatever TensorFlow packages you need. These images tend to be pretty complete. They have pretty much everything you need. The pandas, besides TensorFlow, they'll have the pandas, and some of them will have scikit-learn, so you can do different machine learning stuff too. I'm pretty sure they all have it, to tell you the truth. So I mostly use Singularity images. Occasionally I'll set up my own environment if there's something I need that's not in my image. And that would just be, if you're comfortable with that, that would just be in your, you'd have to just set that up so that when you run your job, you activate those environments. Okay. Finally, one other thing to keep in mind, I do, it's nice to work in notebooks. And if you're running small jobs, you could just always work in a notebook in an interactive node. At some point, if your jobs get longer and you're going with a lot of different variations, you might want to use just a Python script that you can run in batch. So one way to do this, so you go back and forth, is to use this notebook conversion command. So Jupyter has a way to just set up your notebook. You can convert it to a Python script, and you can do this in your batch job. So you can always have a notebook, convert it to Python script, and then run your batch job. And then you always have like the option of going back and forth between running something in batch or running something interactively. So I find when you're developing, it's always best to develop in a notebook. As you get more and more finalized in your code version, then you kind of just mostly want to do batch. But when you're going in between, if you're going back and forth, you can run this convert step. And as long as you have the matplotlib option so that it doesn't try to use the screen, it'll just use a different back end. I can't remember what the AGG stands for, but this says don't try to display it on the screen. And then you can just you can just save your figures in a file. You can go back and forth between notebooks and Python scripts this way. Okay. Oh, GPU. Okay, so on Expanse, and this is the way for other HPC resources on Exceed. The GPU node has multiple GPU devices, TensorFlow by default is always going to run on the 0th GPU device if it's available. And if you're running on CPU, it's just going to use all CPU cores. So you can take your code and just say, all right, give me a TensorFlow image that I know works on GPU, and just run it on GPU, and you'll run on the GPU. What I find is, oops, sorry about that. So what I find it's nice if you're going to run GPU, you don't have to necessarily change your code, but it's nice to add a little bit of snippet so you know what's happening, what devices are available. So this is a code snippet that you can use so that when you run on GPU, it'll show you, oh, this is the GPU devices that I have, the number of GPU devices, and these are what they're called. If you want to start using multiple GPU devices, if you want to actually start splitting your data so it can take advantage of multiple devices, you can do that as well using the mirrored strategy. And I don't have a detail for that, but the Keras tutorials will show, they have pretty decent examples of how you just do a basic mirroring. And you can get some speed up for that. It's not, it's not as big of a speed up as when you go from CPU to GPU, you get a big speed up doing that. When you go from one GPU to multiple GPUs, as long as they fit in memory okay, you'll get speed up as well. Okay. I think that might be, oh, so here's an example. So this was an example with just a multi-layer perceptron with dense layers. The red line is a GPU with different number of units. And you can see the blue line are the CPU with different number of units. And, as I increase my layers for 1,000 units per layer, I start getting a nonlinear increase in time. But I'm still, this particular job was using, let's see, 1,000 units. I was running 25 epochs, 12 layers. I think I had 80,000 by 200 data matrix. And, 4 seconds is still pretty fast. So like for this problem, the difference between the GPU is a lot faster, but it doesn't make such a big difference because the CPU is still pretty fast. It only made a big difference though if I started running a lot of different hyperparameter searches. So depending on, the individual jobs are pretty fast even on a CPU. They're, as you can see on a GPU, more layers, I'm just getting a linear increase. It's not really, there's no nonlinear increase in the amount of time. So it's running really fast on the GPU. But again, so like the total time, the wall time doesn't make a big difference for one job unless I'm going to run a lot of these. But that's the kind of thing you might come across. So the GPU is always faster. You do typically have to wait more time in the job queue. Again, I don't want to say how much time that is. I find like when I've been using actually Bridges lately, and on that system, sometimes I wait just a minute and on my GPU job is going, and sometimes I have to wait, 30 minutes. Expanse seems to be a little bit faster, but again, it could also depend on what the workload is like on the system. Okay, but you do get to the point. You do get to the point where you're always gonna, once you get to a larger network, you're doing some of these vision networks, you're just gonna pretty much always want to use a GPU. Okay, I think that's my last slide.
Yeah, we have a lot of questions that I think we should try to answer. I'm trying to go back to when they first started with sharing code. Yes, we're going to put that on with the video. Can you elaborate on batch size and how it is determined? Did you answer that question yet?
Yeah, I think so.
Okay, and so then is there any specific setting in neural networks to deal with class imbalance?
That's a good question, and the answer is there is a way when you train. Let's see if I can go find this in the fit function. The fit function has an option to resample to put a sample weight on all your training, so you could tell it. Sample, all the classes that are 1, sample it higher than all the classes that are 0. So you take your rare class, assuming that's the positive case, and you just give it a higher sample. That's one way to address it. The network will overfit those samples. That may or may not be what you want. That may or may not be, you know, the kind of thing that's good to do. It can be good if you, in certain situations. And other than, you know, otherwise, like inbound data requires, you know, different ways to I don't know. There's several different things you could do, but not necessarily just for neural networks. So the fit function has that option to resample. That's probably the simplest thing you could do. But using an ensemble of networks will help. And then anything you do that's related to what you do for any model.
Okay, so next question. While working with large data
Before
sets.
that, sorry, can I ask another question regarding the previous question?
Okay.
So in the previous line in my model compile, it would also work to change the metrics to sensitivity, right? So imagine that your like the classes that are smaller are gonna be the positive cases.
You know what? You have the option of using all the standard metrics right there. So you can choose sensitivity, recall, precision, or the precision recall area under the curve is also available. So that's right. So you can also, but I think that's really more problem specific. Like, you know, if you have a rare case, let's say you're trying to predict cancer and it's very rare and the cost of getting it wrong is very high. So then in those cases, you do want to, you know, choose something like sensitivity instead of just accuracy. Correct. Yeah.
Thank you so much.
Great questions. Okay, next one is, while working with large data set, what is the easiest way to upload and access the data from the Jupyter Notebook?
Well, and remember, Jupyter Notebook is just running on Expanse. So you want to, you know, you still want to be comfortable with having access to your Expanse shell command, and just, you know, don't upload your data through the notebook, but upload your data through you know, SCP from wherever your data is. So that's really the best way to do it, is to just get comfortable with the Unix shell, so that you can, you know, you can do wget commands, you can do get clone commands or whatever.
So pre-stage the data, right?
Pre-stage your data, yeah, onto Expanse.
All right, so then another question, the next one is, so this is just a webinar where we watch but not follow along using a teaching project with a number of SUs. Can we do this offline after the webinar? I can also help answer that. We have the interactive videos. We'll put this up. You'll be able to follow through the talk, and then it's expected that you'll take the sample notebook and run it on your own.
That's right.
Paul?
Yes.
Anything else?
That's right. Yeah,
we'll try and add some, you know, maybe some guidelines on that, on how many you just want, one CPU or more. But I don't know what Paul's code looks like.
You can get trial accounts, right? What is it called, Mary?
Yes, startup.
Anybody,
you can get startup allocations, and then short-term trial accounts, and you can find that on the Expanse user guide.
That's right. That might be the best place to start in some sense. Look at how you get the startup or trial accounts for Expanse. You get your trial account, and then you can just run this. You know, get interactive access through the notebook, through the portal as well. You know, you can copy things into your account, and that's really the best way to do it.
We'll include the code. Somebody asked about that, along with links to the PDF, and then a copy of the notebook later on. So there's another question here. I'm going to try and get through these. We're running a little late, but it's up to Paul if he can still stay. How to test if I'm overfitting with my deep learning model. Say I don't have a large data set at that point. My neural network would quickly learn all the features, therefore chances for overfitting are high. How to avoid overfitting, or how to test if my model is overfitting?
I mean, again, you know what cross-validation is. If you don't have much, if you have enough data, you should always do cross-validation. What is cross-validation? Remember, cross-validation is the main thing we do to get an estimate of our generalization error, our estimate of our error when we see new data. So if you really don't have enough data, and I mean, if you don't have enough data to do cross-validation, then what are you going to do, right? And so then you have to start thinking about, well, what do other models do? So there's the penalty methods. You really have to start looking at loss functions that add the penalty function to a loss function, like you know, the L2 penalty or the L1 penalty. So you're really coming up against, when you don't have enough data, you're coming up against, well, what would happen if I use a lasso, for example, or what would happen if I you know, do one of these other models like a support vector machine, which typically works better with less data. Maybe not. So it's a trade-off, right? The neural network advantage is that it might do feature discovery. You know, some of these other models might be better because they build in regularization. So you have to kind of think about, well, I can do some of that with the network. You can build smaller networks. You can build, you know, bottleneck layers. Instead of using 5 units in your hidden layer, use 2 or something like that. So you have to start building in those kinds of regularizations in your design, number one. And you still need to think about, like, how are you going to get an estimate of your generalization error? And that's you know, that's the other thing that helps you with networks, is doing cross validation will help you avoid you know, some overfitting.
Okay, so question about sharing the YAML file with them. I assume that we can do that.
Yeah, I could put that up somewhere. I mean,
Okay.
if you looked at it, it really is just a label, a colon, and some value.
Excellent. All right, so another question. Do we need to upload a Singularity image, or can we create Singularity image on the login node? I tried to follow instructions and it didn't work.
No, so we have Singularity images there already on Expanse. So the system folks sets up our images that are basically there with typical packages, typical environments that we are going to want to use. So you don't want to try to set up your own Singularity image on Expanse. You want to use the ones that are there. If you want to use your own, let's say something different besides TensorFlow, or TensorFlow is something that's new or different, or some other package, then you can use Python virtual environments. And to set those up, I don't have any instructions off the top of my head, but if you look up, you know, it's actually not that many steps to set up a Python virtual environment. And then you can set up your job to point to that virtual environment by, you know, you run a so-called activation step.
So we have Marty. Marty, he's our Singularity expert, and he's posted some information. Do you want to add anything to Paul's comments, Marty?
Yeah, hopefully mic's working. Can you hear me?
Oh, Marty, your audio is echoing. So you could try it again, but otherwise you could just type your responses into the chat.
Better?
That's much better.
Yeah, sorry, I was on my AirPods. For some reason, they don't work anymore. Yeah, so the question was about Singularity. Yeah,
making Singularity.
Yeah, so as I pointed out in the chat, you know, we have a location. I'll paste it again here, maybe, where we have predefined containers, as Paul mentioned, and so you can definitely check those out there. If for whatever reason they don't meet your needs, you can always contact us. Oops. Okay. And I think one comment I would make in terms of if you're going to set up your own environment on Expanse, and especially with running, say, TensorFlow or PyTorch on GPUs, we generally would recommend Conda if you're going to do that, just because then it'll bring the correct version of CUDA that you need for whatever version of TensorFlow that you're installing. If you go sort of the pip install route, it gets a little bit more complicated sometimes. So that's the one thing I would maybe mention.
Thanks, Marty. We're getting lots of questions, but I think we're going to have to cut this off in about 4 minutes. So we'll try to go through these quickly. Question, many computer science people say a neural network is the best method to use on medical record data to predict which treatments will be better for a new patient. With hundreds of potential features from the record, physicians say they can't trust what's happening in a neural network. How do you respond to them because they don't trust what features it's using? Random forest makes sense to them.
A random forest or decision tree? Because a decision tree, a random forest has sometimes the same issue, right? Except it'll give you variable importance. So you do have ways of neural networks to try to see what are the important variables, for example. What I tell people is I would run both. I would say, look, here's what the neural network gives you, here's what the random forest gives you, or decision tree gives you, and sometimes their answers are the same, and sometimes the answer is going to be a little bit different, and that's when you say, okay, well, the neural network might be doing something a little bit different. That's a good question. I mean, there's no definitive way to say here's what the neural network does, or here's why it makes this prediction. I don't know if that helps.
Okay. Again, we talked about uploading data, and I'll put a link to a webinar, a presentation on that. To avoid overfitting, one thing that we can do is early stopping and measure the performance on the validation set. If the validation performance stopped improving, we can stop early and avoid overfitting. I think somebody's trying to answer that question.
Yes.
Okay, so can you introduce any good resource book to paper web page to deal with class imbalance in machine learning?
The Keras website does have a discussion of class imbalance. And I can't remember off the top of my head, but the Keras package is integrated into TensorFlow. The Keras package is the library that gives you all these nice neural network functions, so you don't have to code your own layer activations or whatever. And their tutorials are pretty good. They've become really much more complete in the last couple of years. And they do have a discussion on imbalance classification. So that's a good place to start.
Okay.
It's not a great answer. Like what they tell you makes sense, but like no one has a great answer as far as I can tell for imbalanced data. There is a couple blogs that have some nice examples, and if you look up the balanced random forest, a discussion of what's led to the balanced random forest, that's that will kind of talk to you, explain a little bit about why ensembles can help. And someone else gave the answer that if you could generate more samples. So if you could, there's this idea called data augmentation. So if you have certain kinds of data, like images, you can say, oh, I can easily augment these digit images by flipping them so that maybe rotating them a little bit or something like that. So with certain kinds of data, you can augment your data set by doing certain transformations that don't change. They're not going to change the class, but they just give you more variation on what an image looks like. For some other kinds of data, maybe predicting a cancer outcome out of certain number of features, it's probably a lot harder to create your own data or generate samples.
Okay, so I think that might be it for the questions. I think maybe this is a new one. What do you mean exactly by cross-validation for overfitting in a more general context? Do you mean splitting the data into training, test, validation?
Training, I would say yes. The short answer is yes. I mean, the long answer is that you should your validation data helps you choose your hyperparameters. You can use it to look and see, oh, this is, this number of layers works better than that number of layers. But when it comes time to generate an estimate of your error, if you really want to say, well, this model I predict is going to generate errors for new data with this kind of error rate, that's when you want a test set that is put aside, that hasn't been used at all for training. So, and you'd really want that in certain situations. And, in other situations, maybe you're okay with just saying, oh, this is my best, using my validation data, this is my best hyperparameter. And, it does this well. And see if anybody, wants to challenge that or wants to give you a different data set. Well, how does it do on this other data set? I don't know if that makes sense, but ideally you want a test set that is kept completely kind of apart from anything you do with training.
All right, thank you, Paul. And Edwin posted a link to something on cross-validation that people might find helpful. This is great, but I think it's 22 after, so the 56 people who are still here asking questions, this is fantastic. But I think it's time to let Paul call it a day, and you can always just contact him directly. If you need some help, contact the help desk. They're always ready to answer questions. And for the containers, Marty's done an amazing job. Our suggestion is use those if you can, and if you can't, contact the help desk and see if whatever you need could be added to the containers. That way you have something that's supported, dependable, and standardized. So with that, thank you, Paul. Thank you, everybody. And I think we'll call it a day.